Hey guys, what's going on? We're going to take a peek now at the mathematical section of the magnetic fields and electric fields. So I'm going to shoot you guys a couple formulas here and what the units stand for. Okay, again, this is the math portion of the section. So if we have a wire, okay, let's say this is our wire, and the current is flowing this way. Okay, we learned that we could take our right hand, okay, and use it as a tool to figure out the direction of the magnetic field, which actually comes out at a 90-degree angle. So here's the current, here's the magnetic field. So this would be coming out of the paper, and into the paper. Okay, if this were a piece of paper, so it's going like, kind of looking like this. Okay, coming out of the paper, going into the paper. Coming out and then going in. Okay, so we want to know the force on a wire. Okay, so let's look at the formula. Okay, the force felt from a wire is equivalent to the electric current times the length of the wire times the magnetic field. Okay, so this little segment here is the magnetic field jumping around and circling from here to here, here to here. I'm doing my best to draw it. And going back around and coming through, okay, traveling in this direction. Okay, so there is an actual force produced by this wire. So if I had, and we're going to compare it later, but to a different wire, but if we had a force meter here and we put an object here, we could measure the force that it's felt from the wire. So the magnetic, the force felt from the wire is equivalent to the current times the length of the wire times the magnetic field strength. Now we call this, they'll say perpendicular. Okay, perpendicular. Okay, so this is just a matter of taking the math and looking at some questions. So, okay, I'm looking at one of the questions on the notes. Okay, and it says a 0.5, so a length of wire that's 0.5 meters carries a current of 2.0 amps in a direction perpendicular to a 0.3 Tesla magnetic field. It wants to know what is the magnitude of the magnetic force acting on the wire. Okay, so all we would do is just apply this formula. So the magnetic force acting on the wire would be current multiplied by the length of wire multiplied by the strength of the magnetic field. Okay? So after doing a little bit of math, we did the force, okay, acting on the wire would be 2 times 0.5 times 0.3. The force acting on the wire is 0.3 newtons. Okay, let's look at another one. Okay, so here's our second question. Okay, we're given, and I'll read it to you in word form, in word problem form, but basically it says a uniform magnetic field exerts a maximum force of 20 millinewtons. So we got a force of 20 millinewtons on a 0.25 meter long wire carrying a current of 2 amps. It says, what is the strength of the magnetic field? So what we're looking for is B. And so we just have to do a little rearranging here. ILB. So B, the magnetic field, ends up being F over IL. Okay, so we can calculate that if we transfer that over to the problem. Okay, B, or magnetic field, is equal to 20 times 10 to the negative third newtons, that's a millinewton, over I times 0.25. Okay, so after doing all the work in the calculator, we get the magnetic field, okay, of 0.4 or 0.04 Tesla. Okay, and that's a magnetic field. Okay. Okay, so here's a another question. Again, we're using the force as equivalent to current, length, magnetic field. So they're just taking these and they're solving for individual parts of this. Again, this is just a math lesson basically. And if you were to go into more advanced physics, you would understand that in the field you would have to, this would be very, very useful. For you guys, we're just looking at it as a math lesson. Okay, so look, at 0.5, so the force is 0.05 newtons, acts on a length of wire of 10 centimeters, which we know is 10 times 10 to the negative second meters, perpendicular to a magnetic field of 0.30 Tesla. And they want to know the magnitude of the current. Okay, so what is I? Okay, again, this is just rearranging for the equation. Okay, I equals force over LB. Okay, force over length times magnetic field. So if I plug and chug, this is plug and chug. If I plug and chug the numbers, okay, I end up with 0.05 over 10 times 10 to the negative second meters, okay, times 0.3 Tesla. Okay, and then after doing the math, I would get, after doing the math, I would get 1.67 amps is flowing through that wire to produce that force given a magnetic field. Okay? So, one last part to these notes. We're going to take a look again at our picture. Okay, this is, let's say this is the current in the wire. And we know that if I hold my hand up like this, excuse the black hands, I've been writing all day. If I hold my hand like this, I know that the field wraps, the magnetic field around this wire wraps around, okay, kind of like this, okay, in this direction, okay, and again in this direction. Now, we determined that the magnetic field, this B field around this wire, okay, actually decreases as the distance increases away from the wire. So like this B field, it's hard to describe in terms of like the density of the field, but if I were to like make a whole bunch of dots showing like how dense the field is, the field would be the most dense, okay, as we Okay, as we get closer to the field. So the magnetic field increases as we get closer to the wire, and decreases as we expand out from the wire. Okay. So there is a relationship that I want to talk to you guys about, and I'll get rid of this. Okay, so the relationship between these numbers here would be a formula, and I'm gonna stop here at the formula, and then the next video we'll talk about it. The formula is that the magnetic field is given as okay. The magnetic field is given as a unit, a constant here, which is called the permeability of free space. Okay, and actually has a value. I'll give you that value here. This is the permeability of free space. This is equivalent to 4 pi times 10 to the negative 7th. Very weird units. Tesla meters over amps. Okay, so this is a constant you're going to want to write down and have available to you. And be able to use in the formula. Okay, so the magnetic field is determined by the we'll write that down. Okay, the permeability of free space times the current over 2 pi r. Okay, and that 2 pi r has a lot to do with the circle that we saw that the magnetic field makes around the wire. I'm going to stop there for now because I've gone over by about 2 minutes here. So we'll just take down this formula here, and we're going to work with it a little bit in the next video.